All right, this is kind of a classic question in physics, and we've had objects that have slid down ramps before, objects on roller coasters, and what's been interesting for objects like when we've treated objects that slide down a frictionless ramp and different things like that, we've noticed that their mass cancels out, and all objects will reach the bottom of the hill with the same speed, regardless of their mass, because they're just translating, and so all the energy from height gets converted to translational kinetic energy at the end. But now when objects are rolling, we have a little bit of a different factor to take into account. The fact that they're going to roll or start to try to spin, there's a different rotational inertia term for different objects. So we can ask the question, which object will win the race? And we can ask how fast would each one be going at the bottom and different things like that. All right. So we just treat this from a conservation of energy point of view, so it's not too bad, but it highlights some of the important ideas. And so if we take a look, we might have a bowling ball and a hoop, which are racing each other. And each of them has a radius of 20 centimeters, and they race down a ramp through a height of maybe 1 meter. Now, notice I didn't give you the mass. We'll see if the radius is important, and some different things like that to figure out maybe, who's gonna win. All right, so let's take a look. So we would just start from our conservation of energy principles, and we would need to calculate the velocity of each object's center of mass at the bottom of the hill. The one with the larger average velocity over the same length of the track should probably win the race, right? All right, so we're just going to translate all of our potential energy at the height of the ramp into both translational kinetic energy now, because the objects are going to be moving forward, but they're also rolling, so we have to have both our translational kinetic energy and our rotational kinetic energy term. So what we'll notice is that we have to consider, and we have to look up again, what the moment of inertia is for which object. So we'll start with the hoop. Well, hoops were pretty easy. So if you remember, the moment of inertia of a hoop is just m mass of the hoop times radius of the hoop squared. K, right, the constant in front of it is just 1 for a hoop, because all the mass is distributed the same distance from the center. So it's kind of like a point particle. All right, so we have to substitute that term in. So notice we'll have the 1/2 mr squared omega squared. And notice, like we have with other forms of energy, our mass cancels from both sides. So that's why we didn't need to know the mass of the bowling ball or the mass of the hoop. And notice that we don't even really need the radius of each object, because r omega is the translational velocity for that object. So what's interesting is they don't even have to be the same size objects. So what we find out is we get a simplified formula. Once we've put in r omega for here, right, we get our v squared, and we just have 1/2 v8 squared from our regular translational term, and now we have a 1/2 v8 squared from our rotational term. And so you add those together and it's just 1, right? So we just have v squared equals gh, and we can see that if we just substituted 9.8, and if the height of the ramp is 1 meter, we get a velocity of the hoop at the bottom of 3.13 meters per second. All right, now let's take the case of the solid sphere. So we do the problem exactly the same way. The only difference, right, is that the k for a sphere is 2/5. So when we put in our moment of inertia, we're going to have our 1/2 term times our 2/5 mr squared omega squared, and it's the same drill as before. So the mass cancels, and the velocity of our sphere is r omega, and so when we substitute that term in here, we'll end up with a half. Don't forget, you got to keep that half term in there. And then you have 1/2 k, right, mr squared, the 2/5 for a sphere. And when we do that, we're going to get a 1/2 v squared plus 2/10 v squared. So moving right along, right, 5/10 plus 2/10 is going to give you 7/10. And solving for that velocity, it's going to be root 7/10 of g times the height. And the height again is still 1. So we get 3.74 meters per second. So we can see, just comparing by numbers, right, the velocity of the sphere at the bottom is greater than the velocity of the hoop, and since its average velocity would be higher over the same length path, it should win the race. Now, could we come up with a theoretical way that we would always know what this is? So in general, then any shape which we're going to have both rolling, right, and it's not slipping, by the way, it's rolling down the ramp. And we're translating all that potential energy into both translational kinetic energy, right here, And for our object, we'll just put in the general term k mr squared, where k is the constant for rotational inertia out in front of the object. We come up with the expression 1/2 v squared plus 1/2 kv squared, because again, mass will cancel out through the whole thing, and r squared omega squared is just v squared when the object's not slipping. So if we pull 1/2 v squared out, that gives us gh equals 1 plus k, 1/2 v squared. And solving for a general case for the speed, the velocity is the square root of 2gh over 1 plus k. So we can see theoretically that as the velocity will vary with this term in the denominator, and the object with a lesser k will always translate faster and win the race. So that's a fast way to be able to predict which object will win, is if you have the table of moments of inertia, or if you have them kind of commit a few of them to memory. So we can see, since the k for the sphere is 2/5 and k for the hoop is 1/2, well, 2/5 is slightly less than 1/2. So we can see that we can predict that the sphere, solid sphere, right, will beat the hoop to the bottom. So I'll ask you the question: if it was a hoop, right, and it was a basketball, which was a thin sphere, which one do you think would win the race? So be able to make that kind of conceptual prediction and kind of commit that idea to memory, and then that's a really fast kind of conceptual way to understand what's going on with those kind of problems. All right.